Welcome everyone. Today we are going to discuss about linear mappings. Previous class we have seen that three types of linear maps. One is going to be the translation, another one rotation, and the next one was magnification. So in today's class, in brief, what we are going to prove is, in general, any linear mapping is given, we can split up that map into one translation, rotation, and magnification. So we can say that any linear map is a combination or a composition of these three types of basic linear mapping. So before starting, let us see what is the definition of compositions. So recall that if f and g are two functions, then the composition f and g is the function we will represent as f composition g and defined as f composition g of some x is equal to f of g of x. So here instead of x we are having complex number, so it is z we will represent it. So in a similar manner, the image f double dash of a set. So first we are having a set as S and as Z belongs to S, then we will define what is your S dash, that is image of S, and that too we can define as f composition g of Z is determined by first finding the image, then S dash of S under G, and then finding the image f double dash of S dash under F. So in the same way we can define. Now suppose a general linear transformation is given. A general linear map is given, complex map. That is f of z is equal to az plus b is a complex linear function. We assume that a not equal to 0. What will happen if a equal to 0? A equal to 0 means our function will reduces as f of z equal to b. Then it should be a constant map. So we will assume that this a is not equal to 0. So which maps every point in the complex plane onto a single point B. So we will assume that your A is not equal to 0. And we will write this AZ plus B as modulus of A into A by mod A. So what does this means? A mod A is not equal to 0. So we can have such a representation. Now if you are cancelling this mod A and mod A, you will get exactly the same linear function AZ plus B. Now what for you finding like this means, suppose I am rewriting this as A by modulus of A times Z plus B. Then what will happen? First we can consider the whatever the quantity is in the bracket. So inside the bracket what we are having is, suppose I am mentioning this as some g of z. G of z equal to a by mod a into z. Right? Now what about the modulus of this quantity? Modulus of this quantity is modulus of a by mod a. So modulus of a by mod a is modulus of a by 1 by mod a will come. So 1 by mod a is a constant. So get the modulus value is equal to 1. That means this is nothing but a rotation. Am I right? It is a rotation. Now I have found what is my g of z. Right? Next what I am considering is, I am considering this quantity. Okay, now this will represent as some h of z if I am mentioning. So my h of z is equal to modulus of a into g of z. Am I right? Modulus of a into g of z. Here what is given is modulus of a is greater than 0. Right? If a is not equal to 0, then modulus of a should be greater than 0. That means by definition this is nothing but a magnification. This is nothing but a magnification, right? Using definition only. Next what we have to do? We have to add with this, we want to add this quantity b. So gh, let me mention as j of z. So j of z is equal to h of z plus b, right? Now this is nothing but translation. So So how I can express now my f of z? I can express f of z as J composition H composition of G of Z. Am I right? So this will represent J of H of G of Z. Right? Now this is nothing but J of H of G of Z is A by mod A times Z. Right? Now H of Z means I should have A into, now this is equal to J of H of Z. H of Z is mod A into G of Z. Okay, G of Z. So it will become this into G of this thing. So G of this means, okay, you can write this as mod A into A by mod A into Z, like this will come. So I put here H of Z is not equal to this one. This should be mentioned as H of Z as this into Z only, right? Now this will become, I have made a mistake here. It is not H of Z, it is Z plus B. This is mod A into Z, and G of Z is something like this. Okay, so it will become mod A into A by mod A into Z. So this is equal to J of, I will get it as AZ. Now what is J of AZ? J of Z is Z plus B. So this will become AZ plus B. So altogether what we have done is, we have first took an arbitrary or a general linear function, that's f of z equal to AZ plus B. Now we have expressed that as a combination or a composition of J. What is J? Translation. H magnification and G rotation. So this is translation, magnification and rotation. That means any linear map, any linear complex map can be expressed as a combination or a composition of translation, magnification and rotation. So image of a point under a linear mapping. Let f of z equal to AZ plus B be a linear mapping with A not equal to 0, and let z naught be a point in the complex plane if the point W naught equal to f of z naught is plotted in the same copy of the complex plane as z naught. Then W naught is a point obtained by rotating z naught through an angle of argument of A, then magnifying the result by mod A and translated by B. Am I right? So first rotating z naught through an angle of argument of z. From where you got that one? See here. When you are finding as argument means we will get 1 by mod A is a constant. So argument of A times only we are rotating it. Okay. Next is magnification. Magnification is nothing but modulus of A times, and translation plus B is coming. So B. So this description of image of a point z naught under linear mapping also describe image of any set of points S. So we have explained how we are getting that one. Now for example, we can have this map. So as an example, we consider f of z equal to 3z plus I. Now 3z plus I involve magnification by 3. Am I right? 3z is coming and translation by I, right? But no rotation. See, here no rotation is coming. No problem. If we are having a complex linear function, we can split up or we can have a composition of translation, magnification and rotation. If anyone is missing also, no problem. Now put another way, the mapping f of z equal to 3z plus I is the composition of rotation through 0 radian, right? No change now. And magnification by 3 and translation by I. Now if a not equal to 0 is a complex number, the rotation of z is a rotation through argument of a. We have already seen. And m of z is a magnification by mod a, and d of z is the translation by b. Then the composition, as we have examined, T composition, M composition, R of Z is a complex linear function. Now in addition, since the composition of any finite number of linear functions is again a linear function, we will get the composition of finitely many rotations, magnification and translation is a linear mapping. Next one, a complex linear mapping W equal to AZ plus B with A not equal to 0 can distort the size of a figure in the complex plane, but it cannot alter the basic shape of the figure. What does this means? In the previous class we have seen that when you took the mappings, the previous class we have seen that, see, it was a translation. So even though you are translating a square to some other manner, you are getting the same square, right? And next one, we have seen that rotation, right? When you are rotating this line y equal to 0, again you are getting a line. And the magnification case, we have seen that whenever you are having a circle, this was previously existing circle, and when you are magnifying it, again you are getting a circle only. So like that, it can have the complex linear mapping can distort the size. Size may vary, but the basic shape, that is a straight line means it should be a straight line, a circle means it should be a circle, a triangle means it should be a triangle, a square means it's a square, right? Like that only it will map. Okay, now a complex linear mapping can always be represented as a composition in more than one way. That means, suppose you are having a complex mapping, you can note this as a note. A complex mapping f of z equal to 2z plus I. This can also be written as f of z equal to 2 into z plus I by 2. Therefore, a magnification by 2 followed by a translation by I, right, is the same mapping as translation by I by 2 followed by a magnification by 2. Now let us examine what should be the image of a rectangle and next a triangle under a linear mapping. So here is the question. Find the image of the rectangle with vertices minus 1 plus I, 1 plus I, 1 plus 2I and minus 1 plus 2I under the linear mapping f of z equal to 4iz plus 2 plus 3I. Okay, so let us see how we can find this image. So first of all, we will say that S is the rectangle with the given vertices. So S is the rectangle with the given vertices, and S dash denote the image of S under F. So it's a map from S to S dash. This is our F. Now we will plot S and S dash in the same copy of a complex plane. Because F is a linear mapping, our foregoing discussion implies that S dash has the same shape as S, right? Then we are finding image of a rectangle, so the image also should result a rectangle, right? That is, S dash is also a rectangle. Thus, in order to determine S dash, we need only to find its vertices, right? So now we should find the vertices means we are finding images of the given vertices, right? First one is minus 1 plus I. So minus 1 plus I under the mapping, those will get the image. So we have found out all the images of the given triangles vertices. So therefore S dash is a rectangle with vertices minus 2 minus I, minus 2 plus 7I, minus 6 plus 7I, and minus 6 minus I. So when you're plotting this means you get like this. So this one. Okay, so let us see step by step what are the operations we have performed. In linear mapping, f of z is equal to, so our problem is solved here, that is the rectangle with vertices, this is going to be the image. Now further we are splitting this into rotation, translation and magnification. How we can split up this? Now this mapping is a combination of rotation, magnification and translation. How we are finding? First we are finding argument of 4i. So argument of 4i means pi by 2 and modulus of 4i is 4. So fx by rotating through an angle of pi by 2, right? Radian about the origin. So pi by 2 radian above the origin. So what we are going to do? This was the already existing one. Now we want to rotate it by pi by 2. That means the black colored rectangle will result. Next what you have to do? Magnifying by 4 times. So this was the previously existing. We have magnified it by 4 times. Right. Then translating this by 2 plus 3i. So every vertex of this should be translated by 2 plus 3i. So this was the original and we are translating this to this. So this one, the black colored one was the original image. So this started with this blue rectangle. We have ended with this. Started with this blue rectangle. We have ended with this black rectangle. So rotation by pi by 2, where we got pi by 2, just you find what is the argument of coefficient of z, right? So this is the argument of the 4i, that means that should be the rotation. And for translation means this entire thing will come as translation. And for magnification what you have to do is, you have to have this 4i by modulus of that. Right? That means 1 will come. So that is nothing but 4 will come. So that is the magnification. Now a linear mapping of a triangle. So find the complex linear function that maps the equilateral triangle with vertices 1 plus I, 2 plus I and 3 by 2 plus 1 plus 1 by 2 root 3i. Right? Onto an equilateral triangle with vertices I, root 3 plus 2i and 3i. So let us have the solution. Let S1 denote the triangle with vertices, given vertices shown in color. That means this was the originally existing, that is whatever is given triangle. And F dash represent the triangle with vertices. What is the vertices? I, 3i minus root 3 plus 2i. See. We want to translate like that only. Okay. So we have plotted that two rectangles. That is, this was the existing one. Now its image is this one. Right? Now we want to find what is this mapping. We first translate S1 to have one of its vertices at the origin. So what you're going to do is, first we will translate this to the origin, because any one of these vertices at the origin. So if we decide that the vertex 1 plus I, so 1 plus I means this point, 1 plus I should be mapped onto 0, then this is accomplished by the translation t1 of z equal to z minus that complex number, that is 1 plus I, right? So we are using this t1 of z and we have translated this given rectangle into a given triangle into a triangle whose one vertex is the origin, that is this. We have translated this point from this side to here. And let S2 be the image of S1 under T1. So this is here S2. This is here S2 now. Then F2 is the triangle with vertices 1. Similarly, you can find what is the translation from here to here. So the images should be 0, 0, 1, 0, and here one more will come. Okay, and that is 1 by 2 plus 1 by 2 into root 3i. Now from those we see that the angle between the imaginary axis and the edge of S2 containing the vertices 0 and 1 by 2 plus 1 by 2 root 3i is, that is this angle. This angle we can see that this is going to be pi by 6. Okay, so this is going to be pi by 6. Thus, rotating through an angle of pi by 6 radian counterclockwise about the origin will map S2 onto a triangle with two vertices on the imaginary line. Am I right? So, this is pi by 6. So, suppose you are rotating this to pi by 6. Pi by 6 radian means you will get this rectangle, this triangle over here. Right? These two vertices will lie on this imaginary axis. So that only we are going to do here. Thus the rotation through an angle of pi by 6 radian counterclockwise about the origin will map S2 onto a triangle with two vertices on the imaginary axis. See, like this. This was previously existing one. Now we have converted or we have rotated that to pi by 6. So we will get a triangle like this. Now this rotation is given by rotation of z equal to e raised to I pi by 6 into z. Okay. Now it is easy to verify that each side of the triangle S3 has length 1. It's true, right? Okay, now because each side of the desired triangle S dash has length 2. Next what we are going to use is desired triangle means because each side of the desired triangle S dash is of length 2. Since it is given, we want to find the map that will map this triangle into this. So we take any two vertices of the required triangle. This is 1 root 3 plus 2i and 3i. You find the distance. So when you're finding the distance from I and root 3 plus 2i, you will get it as 2. Right? Because this square plus this square, right? You will get it as 2 itself. So like that you can find, easily you can find these two. 3 square, right? You get 9. And this one 1, right? So like that you can easily find out what is the distance between these vertices and all. So we have seen that the required triangle is of magnification 2z. So we will introduce the magnification as 2z. Map the triangle S3 shown in color, that is blue color, onto a triangle S4 with vertex like this. So what we are going to do is just we are magnifying this by 2 units, right? So this side also 2 units and this side also. Finally, we translate S4 by I using the mapping T2 z equal to z plus I. Because one of our vertex is I, right? Not 0. Our required triangles, one vertex is I. See, vertex 1 is I and this is 3i. That means it should lie on the imaginary axis, these two vertices. That's why we have translated that vertex to our imaginary axis. So this is our this one when you are translating, this should be your I, this is your 3i and this is the other vertex. So in conclusion, we have found that the linear mapping f of z equal to like this, T2 M R T1 composition of this. So the mapping is like this: root 3 plus I into Z plus 1 minus root 3 plus root 3I. So this is the required map. So in today's class we have seen that any linear mapping can be considered as a combination of or a composition of rotation, translation and magnification. So with this, I'm winding up today's session here. Thank you for your patient listening. Thank you.